All right, welcome back. We're going to take a look at measuring a wave part 2. Now, last time we went over just one equation because we were still covering a couple of wave properties. This measuring of a wave part will focus mostly on equations. We're going to cover 3 more equations today, and we're going to get familiar with how they work and why they work. So, first of all, there are a couple of things that we need to know about waves before we get started. So here, we want you to know the difference between a pulse and a cycle. They're sometimes used interchangeably to mean each other, so there's a difference that you need to know in order to better understand how these equations work. A pulse is a single vibration of sound, whereas a cycle is one alternation of pressure, or alternation of the wave in this case, like a crest and a trough make one cycle. So I have two pictures here. This picture here represents one pulse because it's a vibration. It's also one cycle because it's an alternation between one up, one down, one crest, one trough. So this picture down here on the bottom left is both one pulse and one cycle. The second picture here, this is also one pulse. It's one vibration that's occurring. And you can see these happen pretty much right after the other. And then there's a lot of spare time out here. We call it listening time in the ultrasound machine. But this would be one pulse, but two cycles. Two cycles, because you can see that there's an up and a down, and then an up and a down again. So there's two alternations of a crest and a trough. So that would be two cycles, but one pulse. So again, this one bottom left, one pulse, one cycle. This one is one pulse, two cycles. And that's going to be crucial because when we get into the equations we're covering today, you'll have to know what those mean, especially for word problems. If you're reading a word problem, you need to know the difference between a pulse and a cycle. All right, now that we got that term down, let's take a look at measuring those cycles. So what kind of data can we gather from these waves? The first one we're taking a look at is period. Again, we can't use the letter P because that's used in other physics equations, so we're going to use the letter T. Think of T for time because period is a time measurement, and that's going to help you better understand why this works. So period is a time measurement. And period is the time it takes for a complete cycle to pass a point. As frequency increases, period decreases. We'll cover the second sentence in just a second. We want to focus on the first one. The time it takes for a complete cycle to pass a point. So remember that a cycle is an alternation of a crest and a trough. So however long it takes for that wave to have one crest and one trough, that is the period. So the time it takes for one cycle to occur. And we're going to measure that in microseconds. Now, when we go back to that second sentence, as frequency increases, period decreases. Remember that frequency is how many waves we can get to cross a point within a second. A higher frequency means that we have more waves crossing that point in a smaller amount of time. So remember that period is a time measurement. Think of a runner. If you are running a mile, the faster you run, the lower your time. So if I run 1 mile in 10 minutes, then that's actually pretty good. But but if I ran that same mile faster, I would still be running that same length, but I would have a smaller time because I'm going faster. My speed is faster. In the same sense here, if your frequency is higher, then the amount of time it will take for that cycle to pass that point is going to be lower. All right, hopefully that makes sense. And you can see we have our moving image here. The red dots are the beginning or the end of that cycle. So you can see this time period, or this period being measured here. Okay, so that is period. Now let's take a look at pulse duration. Pulse duration. Remember what we talked about with a pulse? A pulse is a vibration of sound. So pulse duration, duration just means how long it lasts. It's another time measurement. So pulse duration is the time it takes for one pulse to occur. So the definition is actually in the word itself. Duration is how long something takes, and then we're talking about pulses. So the pulse duration is how long it takes for one pulse to occur. So we have here in our diagram, we have two pulses. We have one pulse here, one pulse here. And the period, remember, is that one cycle. So we've got 1, 2, 3, 4 cycles here. So we can measure 4 different periods, if you will. But if we combine all of them, how long this entire pulse takes, that is the pulse duration. That's why the equation for pulse duration is the period times the number of cycles, because the period is how long it takes for one cycle to occur, and then that same time measurement is going to apply to every cycle in that wave. All right, so that is pulse duration. So how long does it take for a pulse to occur? The next one is pulse repetition period. So again, if we break down the word, repetition means how long does it take for it to repeat itself? How long does it happen till how long does the pulse take for the next pulse to happen? And that's exactly what it means here. The time it takes for one pulse to occur until the next pulse occurs. So we have our same 4-cycle pulse here. The pulse duration is how long it takes for the entire pulse to pass. And then if we add the listening time in to that time, then we get the pulse repetition period. We get the period of time that it takes for the pulse to repeat. So that is what pulse repetition period is. How long does it take for one pulse to finish until the next pulse begins? All right. Hopefully those all make sense. I've got one more definition for you before we launch into our equations, and that is pulse repetition frequency. Now, this one is very similar to the frequency that we learned about in the part 1. So pulse repetition frequency is going to be looking instead of at the wavelengths, because remember, frequency, just frequency, is when we're measuring how many wavelengths we can get to cross a point in a certain time, in 1 second usually. Pulse repetition frequency is how many pulses we can get to occur in 1 second. That's the big difference. So if this graph here, if this entire line from this end all the way to this end represented 1 second, the number of pulses that are in there would be the pulse repetition frequency. How many times did the pulse repeat in that 1 second? So this one would have a PRF, or a pulse repetition frequency, of 3, because 3 pulses were able to occur within that time limit. So a pulse repetition frequency is going to be measured just like our other frequency. It's going to be measured in hertz. And that's how many of these things can pass within a second. In this case, pulses. All right. Hopefully those all make sense. We're going to launch into some equations now. Dun, dun, dun. All right, I'm going to adjust my screen really quickly so we can write these down. There we go. All right, so we have our period, which we represent with a T. And this time I'm going to write down the units as well, because I know last time when we did wavelength and frequency, we had to remember what the units were when we were doing our word problems. So I'm going to write down the units in our equations here. So T, or our period, measured in microseconds, equals 1 over the frequency, which is measured in megahertz. All right, our pulse duration, how long a period lasts, measured also in microseconds, is the number of periods, or the length of the period, the time length of the period, times the number of cycles. And the last one, our pulse repetition period and our pulse repetition frequency are related. So our pulse repetition period, which is measured in milliseconds, that's a crucial difference here, milliseconds, is 1 over our pulse repetition frequency, which is measured in kilohertz. Don't get these confused. This is really the only frequency equation that we're going to be using kilohertz in. And you can convert them, but that's a little complicated, so I'm just going to teach you how it is. All right, so the pulse repetition period in milliseconds is 1 over the pulse repetition frequency measured in kilohertz. All right, now that we have those equations, let's take a look at some example problems. Example problem number 1. A wave with a frequency of 40 megahertz is produced from the transducer. Calculate the period. Fortunately for us, this is a simple plug and chug. We know, okay, so first we have to identify what are we solving for. It says calculate the period. So we know that we're going to be using a period equation or an equation with period in it. Fortunately, we have one. It's just period, again in microseconds, equals 1 over the frequency, which is measured in megahertz. All right, now we have to figure out what numbers we have in our equation. We have the number 40 megahertz. And good for us, that's the only number we really need in order to solve for our period here. So the period is going to equal 1 over 40. 1 over 40. So that means that our period is going to equal 0.025 microseconds. That would be my period. And voila, we have that. We're done. That means, so what does this equation mean? What does this number mean? It means it takes 0.025 microseconds for one cycle to occur. That's what that means. All right, that was our first example problem. Here's the next one. Okay, we're going to switch it up here. We're going to go to the pulse duration. Remember pulse duration? Pulse duration is going to be our period times the number of cycles. So I'm going to write that again. Pulse duration in microseconds is going to equal the period in microseconds times the number of cycles. All right, awesome. So we're looking for pulse duration, and do we have cycles? Yes, cycles are indicated here. So what is a pulse duration of a 2-cycle pulse with a frequency of 35 megahertz? Okay, so we have the number of cycles. We know that n equals 2. And that is just a number. It doesn't have any units because that's how many there are. Kind of like I have 2 apples. In this case, we have 2 cycles. And we have a frequency of 35. Now hold up a second. We can't use frequency in our PD equation, in our pulse duration equation. So now you have to think to yourself, okay, well, now what do I do? Now what do I do? I have the number of cycles and I have the frequency. So how am I going to use that information to get what I need in order to plug it into this equation? Remember that T period has an equation of its own. In order to find period, we'll have to use the frequency, the numbers that we are given. So remember that period is 1 over frequency. So another way that we could write this equation so that it means the same thing is simply PD equals 1 over F times N. Because this value and this value are the exact same thing because of this equation. So you can substitute those. Or, if you're going to make it easy on yourself, you can simply solve for period first and then plug it into the equation. You can do it either way. But this way might help you better understand the relationships, because what does that mean now? what would happen to this wave? I'm not going to give you the answer, but I want you to think about this. What would happen to the pulse duration if I were to increase the frequency? What would happen if I decrease the frequency? Now that you have this equation down here, you can find out. You can know. Okay, so let's do it the slightly easier way, and let's solve for period first. And let's get a number, and then we'll plug it into the equation. So if I have 1 over frequency, so I have 1 over 35, can I plug that straight in? Let's check our units. 35 megahertz. Can I plug that into the equation? Yes, I can, because the megahertz is what we need the frequency to measure in order to get microseconds out of period. So we're good there. Make sure to always double check that. So 1 over 35, and that's going to be 0.029-ish. 0.029. And now we're going to remove this part of the equation and we're going to replace it with the number that we got. All right, and then we're going to remove that n on the side here, and we're going to replace that with the number that we were given, number 2. All right, now all we have to do is chug out the numbers. So we have 0.029 times 2, 0.058. 58. Fabulous, and that is in microseconds. All right, fantastic. And that's how you would calculate the pulse duration from this equation here. All right, so that's example problem number 2. Let's take a look at example problem number 3. Number 3 says, what is the pulse repetition period for a pulse with a pulse repetition frequency of 341 kilohertz? All right, so this one looks pretty complicated, but it's okay. We can break it down into pieces, and it's actually not that bad. So first, what are you looking for? What are you trying to solve for? In physics equations, that's going to be the most important thing for you to ask right off the bat. What am I solving for? It says, what is the pulse repetition period? So I'm looking for the PRP. Okay, now do we know any equations that use PRP? Yes, we do. It's 1 over PRF. But there was something weird about this equation that I told you to remember. What is that? It was the units. PRP is measured in milliseconds, the weirdo, and PRF is measured in kilohertz. Why is that important? Because if we're not given these numbers in this format, we have to swap them out in order to get the right units. You have to convert them. All right. So that's the weird thing that I told you to remember. Now let's continue analyzing the word problem to see what we've got. So it says for a pulse with a pulse repetition frequency of 341 kilohertz. So that's the only number we have. Fortunately, that's the only one we need. So all I have to do is plug it straight into the equation. PRP equals 1 over 341 kilohertz. So if we were to plug that into our handy-dandy calculator, we get 0.0029. 29. And what are my units again? Milliseconds. Yes, milliseconds, because PRP is a weirdo. All right, there we go. And that is our answer here for our pulse repetition frequency. Or, I'm sorry, for a pulse repetition period. All right, fantastic. So what does that mean? What does PRP equals 0.0029 milliseconds? What does that mean? That means that the length of time that it takes for a pulse to occur until the next pulse occurs is 0.0029 milliseconds. So it's really fast. Okay, awesome. I've got one more problem here. I want you to solve it. I'm going to go back to our whiteboard with the equations so you have them. There we go. So example problem number 4, a transducer probe produces a 10 megahertz frequency with a pulse repetition period of 25 milliseconds. What is the pulse duration and what is the pulse repetition frequency? Take some time, pause the video, solve this equation. Again, if you're having trouble, let me know.